I'm assuming you've read the video title. Yes, I have approximated sine of x using only redstone, but I think before we actually get into that, it would be helpful to understand what sine of x actually means. Now, I'm pretty sure we're all acquainted with a right-angled triangle and its sides, especially the hypotenuse. I'm also quite confident that everyone watching this would also know the Pythagorean theorem that a squared plus b squared is equal to c squared, which really means that a square of side length a summed with a square of side length b would have a combined area equivalent to a square with a side length of the hypotenuse. Getting back to my original point, the side of an angle is really just a ratio, or a division, of the length of the side opposite to the angle and the hypotenuse of the triangle. Putting this into practice, say I have a right angled triangle with an angle of 30 degrees. Now, the hypotenuse of this triangle has a length of 4, and the side opposite to the angle has a length of 2. Substituting that into our function, we get that sine of 30 degrees is equal to 2 over 4, or simplified, sine of 30 degrees is equal to 1 over 2. But how am I going to do this with redstone? I mean, clearly it's not feasible to draw up a million different triangles, all with different angles, then dividing the lengths by each other and saving that in some huge lookup table. Clearly, there's another easier solution. Well, actually, two other easier solutions. Now, of course, me being me, I decided to go with the longer, more complicated solution, and in this following segment, I'm going to explain what it is and how it works.
Now, the method I'm about to explain is called the Taylor series. No, not that Taylor, this Taylor. And it's the method in calculus used to describe functions which normally can't be easily described. Functions like sine of x, for example.
The way it works is that for any function, not just sine of x, we analyze how fast the graph is moving at that point, otherwise known as the derivative, and use it to create a term in an expanding polynomial. Now, something important that you do need to know is that in mathematics, a series is just an infinite sum of numbers that follows a pattern, which is described by the term in front of the summation symbol. For example, here's a series called a harmonic series. Essentially, what we do is we solve the equation for k is equal to 1, then we add the solved equation for k is equal to 2, k is equal to 3, k is equal to 4, and so on. Now, we're finally getting into the part where I explain how I'm going to do this. This is the Taylor series for sine of x. And just like before, it describes a pattern which very closely approximates the graph of sine of x. Now, in front of you, the yellow graph is the actual graph of the function we're trying to approximate, and we're going to see how adding more and more terms from the series in the top left gets us closer and closer to the yellow graph. So, our first term simplifies to x over 1, which is also just x, and graphing that, you see we get that first diagonal part of the sine of x graph. Now, our second term gets us minus x cubed over 6, or minus x cubed over 3 factorial. And we can start seeing how this blue line, this blue graph, gets slowly closer and closer to the first quarter of the graph. And there you go. You see now we've covered that section from 0 to 90 degrees, or 0 to negative 90 degrees. And we can see how adding more and more terms to this series just makes it closer and closer. Now, I'm going to stop doing the actual math and just going to show you how the series expands. And we can see that each time the polynomial gets really close to the graph and just starts tipping off. But wait a second. Rewind that. I'm not creating an infinitely large polynomial for some silly redstone project. I need to set some sort of limit onto this. How about 90 degrees? Because that's just above the largest possible angle that you would see in a right-angled triangle. Looking back at the Taylor series, we can see that calculating the polynomial up to the third term gives us a really good approximation up until 90 degrees, after which it starts deviating a little bit. I mean, look at this. This graph is the graph of sine of x, this is the Taylor series approximation, and this is the difference between the two at every single point. The higher this purple graph is, the more incorrect our approximation is at a given point. Now, we can see that from 0 to 90 degrees, the purple graph lays extremely close to 0. And just after we get past the 90 degree point, the inaccuracy starts rising. I'm going to be honest, I don't want to edit this video anymore. and I don't want to do any more animations, so I think I'll just get straight to the point, and we'll start off with showing the actual machine in use, and then I'll do the showcase that I always do. It's like 4 a.m. right now, I'm really tired. Let's get started. I think I'll just choose a random number between 0 and 90. What about 76? 64 plus 4 is 68, plus 8 is 76 degrees. Okay. Now what'll happen is this gets multiplied by 3,141. Alright, so 3,141 is the constant we use, and ignore that. This then gets thrown into a huge division, which is basically 3,141 divided by 180,000. And that's basically what the end of this division basically brings about the actual radians conversion for our degrees values. So it's pretty important that we do this. Pause. I just want to make sure that before we continue, radians is a different type of measurement system. It's not degrees, but it is used to measure angles. It's just a different system. So don't get worried about what is radians. It's just another way of expressing an angle. And the thing is, this build is so big that I have to load every single part individually, which is why it takes so long to get a result. Have a look. Results are changing over here. Alright, next step would be to multiply x by itself. So, if you remember, the Taylor series goes x minus x cubed over 6 plus x to the 5th over 120. So, x itself is just whatever's the binary is that's stored in these blue lines. So all we have to do is make sure we maintain one copy of that, and it'll get maintained over this way. But to get to x cubed and x to the 5th, we need to at least get to x squared. The value stored in these redstone lines is the value of x squared. Now, we all know that x squared times x is just going to equal x cubed. So we'll just multiply it by x again, and you'll see that we do that. So this is the x line, remember? And the x squared line goes down here into this multiplier. Meanwhile, our x line has been inputted into this multiplier from here. And notice this is how we input into our multiplier, just to show you. So we've done x times x squared, right? Which means that if I just take a piece of orange wool, everything over here, from top to bottom, is going to be x cubed. So this is the x cubed value. So I might as well pull out a sign. Right? Now, considering we have x cubed, I said I would find it easier, instead of building two more multipliers, so this one and then the next one, so to go from x cubed times x is equal to x to the 4th, and then we do x to the 4th times x is equal to x to the 5th, which is what we're looking for. You know, the laws of exponents, basically. We can just do x squared times x cubed, which will also equal x to the 5th, right? So this is where our x squared value, which we brought over from earlier, comes in handy. So we input that, and then we input x cubed, right? But not before saving a copy of x cubed, which comes around this side. Then it's really easy. All we have to do, first of all, like, take the output of this x to the 5th. This output is x to the 5th, remember? Take that output and input it into a divider. So this output has to get divided by 120, because if we remember, our polynomial says x to the 5th divided by 120. So I just input 120 with redstone blocks here. And then our x to the x cubed value, which is over here, I had to divide this one by 6. So remember, x cubed over 6. So that's easy enough. And we take the outputs. So this line is x cubed over 6, and I can't find it actually. This line is x to the 5th over 120. This line, which represents what term? X cubed over 6, which is x to the 5th over 120. This line which is just plain old x. So what I ended up doing was I took the x value, I wired it, and then I added it to the x to the 5th over 120 value. So this is the addition. And this gets added and everything, and it goes into here. This value here would be x to the 5th over 120 plus x, right? And the last step would simply just be subtracting x cubed over 6, which is what we do here with the subtractor. This is the final result of sine of x, right? But the problem is it's written in binary, so all I did was I converted it from binary into, decimal with this huge binary to BCD. And this is the final output. I'm gonna do system set night to make it easier to read this. But have a look. This is what it thinks sine of 76 is. And I'm going to hope that that's correct. So sine of 76 is 0.97. And, okay, I mean, we're wrong by quite a bit here. But I would say, yeah, when we get closer to the values near 90 degrees and near 0 degrees, the values do have a little bit of inaccuracy in them, so I think, like, I can't really do anything about this, but 0.98 is really quite close to the actual correct answer, so I feel like it's not nothing to be that mad about.